So last time we introduced Landau's free energy functional as a function of order parameters in power series of these order parameters. And we could use it to describe various transitions such as the Ising transition. So today we will study in more details how this phase transition occurs in Landau's formalism. So first of all, let's introduce this L, which is Landau's free energy density that we introduced earlier last time. And we know that due to the symmetry in the absence of the field, external field, this L is actually symmetric with respect to the phi. Therefore, all those odd powers of phi disappear. And so we have only left with the even powers of phi in this expansion. And we can shift this constant term A0 as just a constant energy shift. And we don't care about this. And this is the simplest possible Landau's free energy density we can write down near the phase transition, okay, where this A and B coefficients are both positive. And we know that B should be positive in order to actually have the minima value of the Landau free energy, and it can actually prevent us from unbounded below, okay, that kind of an unphysical situation. So at h equals 0, we could find the solution of this non-zero magnetization or order parameter by minimizing the Landau's free energy density with respect to phi, and we get a trivial solution phi 0 in any case. So when temperature is above transition temperature Tc, we don't have any mean field order parameters, which is finite, and phi is 0. And when temperature is below Tc, we get finite order parameter developed, and that value is given by this kind of a mean field equation. And again, this little t is a dimensionless temperature relative to the Tc, and when little t is negative, you get one more negatives. Therefore, it is positive because A and B coefficients are both positive. Okay, so you get finite magnetization or mean field order parameter developed when temperature is below Tc. And we could also calculate the energy of a Landau's free energy density at that different solutions. For example, in this disordered phase, when little t is positive, this L, when phi is 0, is actually exactly 0. But when we're below the transition temperature, this L takes the negative value. So we will make a plot of this L in different cases in just a moment. So then we could calculate all these various mean field critical exponents predicted within this Landau's mean field theory that we already obtained earlier by other methods. So first of all, this magnetization is a function of little t to some power with the exponent beta, and we know very well that this is a square root behavior, and therefore beta is 1/2. And second quantity is a specific heat, which is the second derivative of this free energy with respect to temperature multiplied by temperature. So which is, in this case, the second derivative is Landau's free energy density with respect to little t, and divided by this Tc. And this is 0 above Tc, and this is a positive value constant below Tc. So you summarize specific heat, which is proportional to t to some power of alpha minus alpha, and here it is either 0 or a constant, and therefore alpha is 0. But we know that this is wrong. This is incorrect. So we will come back to this later. So the Landau's mean field theory just give us some rough estimation of the critical exponents, and those exponents do not depend on dimensionality, which is certainly wrong. And we will include the fluctuations beyond the mean field order parameters to actually fix this incorrect estimations. But at the moment, this is the easiest way that we can get the critical exponents. So another critical exponent is delta, which is the other transition. When little t is 0, this external field behaves as order parameter to the power delta, and in this time, this delta is actually 3, so you could very easily see the dependence of h on phi. So we get everything that we got before. But this is not surprising because we construct this Landau's free energy precisely based on what we have for the Ising model calculation. So this is just a slight generalization of what we have done. for the Ising case. So about isothermal spin stability at h equals 0, we could take the differentiation of this so-called equation of state with respect to the external field, and we get this relation, which is given by, so chi t is given by 1 over this denominator here, which is a function of little t and a and b and the mean field order parameter phi. So we plug in this value of the mean field, both above and below the transition temperature. We get very similar but slightly different behaviors near the transition, which is little t to the power of minus gamma or minus gamma prime. For the gamma, it is above, for the case above the transition temperature, and for t is less than 0, below the transition temperature, you get, in principle, different exponent gamma prime, but in this case, both gamma and gamma prime are 1 because it is just 1 over t dependence. Okay, with a different prefactor. For the case above Tc, this is 1 over a. For the case below Tc, this is 1 over 2a. Isothermal spin substitutability above and below transition temperature is the prefactor in front of this 1 over t behavior. So if I plot this so-called chi plus representing the isothermal spin substitutability above Tc, and chi minus is the same quantity below Tc, and both curves show this 1 over t behavior with a different prefactor which differ by a factor of 2. And this ratio between this prefactor a plus and a minus above and below the transition temperature is a universal prefactor ratio, and it doesn't depend on anything. So experimentally, one can tell this universal ratio by measuring the isothermal spin substitutability above and below the transition temperature. And you can check whether this is 1 over t behavior on both sides. And number 2, you can check the prefactor difference. So that's the very powerful prediction based on this Landau's a little bit naive mean field theory. So let's use graphs or figures to illustrate how the phase transition occur within the Landau's formalism. So here I plotted 9 figures depending on whether this field is negative, 0, or positive, and also depending on whether T, the temperature is below Tc or equal to Tc or less than Tc. So there are 9 situations, and each cases we could use a plot to illustrate how this Landau's free energy density looks like as a function of phi, given the fact that this is the expansion in terms of this powers of phi, but we have quadratic in phi and quartic in phi, and also a linear in phi. So in general, when both A and B are positive, and also H could be either 0, positive or negative, and we could either be above or at the transition or below the transition. So there are 9 different cases that we can study, and in each case we could plot this Landau's free energy density as function of phi. For example, you could fix at H negative and look at this horizontal 3 plots, and you find that for H negative and T above Tc, this L shows a single minima when phi is negative, and which is the kind of a quadratic with a quartic correction, and it shows a global minima when phi is negative. When field is negative but T is exactly at Tc, you get some change in the shape of this Landau's free energy density as function of phi, because there's something going on here. So there seems to have a second minima or local minima develops right here on the positive side of phi. But when T is less than Tc, and this kind of twist and turn on the positive side of phi becomes a true local minima. Okay, but still you have another minima, which is global minima on the negative side. In other words, when field is negative, the shape of the L shows a single minima to the double minima. All right, so we'll come back to this just a moment. We can also look at this central row here. When H is 0, again, when T is above Tc, you get a single minima right at phi equals 0. And when both h is 0 and t equals Tc, you get the single minima right here at phi equals 0, but then the shape changes. When temperature is above Tc, this is V shape. But when T is exactly at Tc, this is a U shape. Notice this subtle change in the shape of and geometry and topology of this L versus phi. And when T is below Tc continuously, you have a double minima L develop near phi equals 0, and the value of this mean field order parameter phi becomes finite, and it evolves from 0 continuously to a finite value, and this connects the U shape of this L right at Tc, because when this shape becomes U shape and right on two sides of this phi equals 0, there's a tendency that this L show the double dips or double well right next to phi equals 0, and the development of this non-zero phi emerges continuously from 0. So this is the continuous or second of the phase transition from phi equals 0 to phi is finite. So this is phi equals 0 as your ground state, but on the right phi is finite, which means that when you cross transition temperature Tc from above, the system develops a double minima continuously, and it emerges from the single minima. And this transition occurs continuously when you cross the transition temperature Tc, and if you are at 0 field. And this is precisely what we studied earlier when we studied the Ising transition at 0 field, and you tune the temperature from above Tc to below Tc. What you will see is that you continuously find a finite mean field or magnetization developed when you solve this mean field equation. Remember that this the intersection between this hyperbolic tangent function, a straight line that we discussed earlier, and right at Tc, you barely find a finite solution, but slightly below Tc, you could find two solutions in addition to a trivial solution at 0, and these two solutions correspond to the value of phi, where this L, the Landau's free energy density, becomes a minima. So in other words, we can roughly consider this Landau's free energy as some kind of free energy, and when there's a non-zero mean field order parameter developed, and that finite order parameter is going to stabilize system, because then this Landau's free energy density is actually the minima, a global minima, when phi becomes finite, which stabilizes the system. And therefore, you can see the previous phi equals 0 solution is not a stable solution anymore, because this, in terms of the Landau's free energy density plots versus phi, is actually a local maxima. Okay, so this is a local maxima. So from statistical point of view, as you know very well, that whenever we have a statistical stable phase or state, it must be a minima of free energy. And this is precisely what happens here. Previously, when there is only one stable solution available where phi equals 0, and this phi equals 0 is actually the global minima of a Landau's free energy density, but when T is below Tc, and this so-called global minima at 0, when T is less than Tc, becomes unstable. And why is it unstable? Because it now becomes a local maxima rather than local minimum or global minima. And instead, the global minimum is actually shift to phi either plus or minus the magnetization. So it is a change of the global minima that leads to the phase transition. So now we learn the lesson. So how the phase transition occurs in terms of Landau's language, it is a change of global minima of Landau's free energy density, and by analyzing the global minima of a Landau's free energy density, you know how the phase changes and where the phase transition occurs. Okay, so this is a very important key point in understanding how the phase transition occurs within the Landau formalism. So likewise, when H is positive, and you get all the situation reversed with respect to the H negative when you across the transition, temperature Tc. Again, so you get finite and positive mean field when T is larger than Tc, and a double minima structure is going to happen when T is at Tc, and when T is less than Tc, you indeed find a double well. But again, so the right well is actually showing the global minima, okay, which means that there's no phase transition if I am in a situation where the field is positive and you go from temperature higher Tc to lower Tc, and the global minima is still on the right. So no qualitative change and no additional minima, global minima or change of global minima occurs. Of course, you have a double minima right here when temperature is below Tc, but the other minima is actually local minima. So in other words, the global minima is still there, and since there is no change in global minimum, there's no phase transition. So likewise, there's no phase transition if I go across the top row from above Tc to below Tc, okay? So now let's look at the vertical lines. So for example, if I look at the right column here, and we study the temperature below Tc, but instead of changing temperature, we change the field. So we go from the negative field to zero field and to the positive field. So if I go from the negative field, but T is less than Tc, we know that there is a double well or double minima, but the left minima is actually the global minima, and the right minima is the local minima. But if I focus on the center, the second figure in the middle, where H is 0 and temperature is less than Tc, and I get an equally double well shape of this Landau's free energy density versus phi, and you can see that my global minima suddenly changes, right, from the left well to actually the double well with the same energy. But then when H is actually positive and I switch the global minima from the left well to the right well suddenly. So why do I say suddenly? Because there's no way that this global minima on the left continuously evolves to the right, because phi equals 0 is never being a minima. So you can never cross the minima point at phi equals 0, because phi equals 0 is never be a minima. So that change should actually behave like a jump. So there's a jump between the global minima occurring on the left side and the global minima on the right. So when you tune your field from the negative value to 0 and to positive value, so no matter how small your field is tuned, there's always a jump of a global minima from the left well to the right well without crossing the phi equals 0, because phi equals 0 is never be a local minima. So it's always a local maxima. So that's what we call the first order transition, where you have a jump of your order parameter suddenly from one particular value to another particular value without crossing 0. So you can see that from these 9 figures that we could have either continuous phase transition going horizontally in the center or going vertically on the right or also on the left. So this is a very important step in order to understand why we adapt Landau's formalism to understand a phase transition, because the phase transition involves the changes of a global minima, and how the global minima changes can be studied or analyzed by analyzing Landau's free energy density, because the ground state should be the global minima of a Landau's free energy. But again, Landau's free energy is not what we usually call the thermodynamic free energy or Gibbs free energy or Helmholtz free energy. No, it's not the same as those free energy that we're familiar with in statistical mechanics. So we will study what is the relation between the Landau's free energy and the other free energy that we are familiar with in statistical mechanics. As I mentioned, we could study the first order transition at a finite field when we cross the transition temperature Tc. So let's just study how this first order transition occurs. Suppose that the field is fixed at positive value h larger than 0, and we know that this kind of a symmetry between L as function of phi and L as function of minus phi is broken down because Landau's free energy takes different value if you change h from this positive value to negative value, because apparently you have a linear term. So any finite field is going to break this symmetry, the even symmetry of a Landau free energy density, a function of the order parameter. So as a result, since we have this linear in phi term already in the presence of fields, why not phi to the power of 3 or cubic in phi term? The phi cubic term is allowed in this Landau's free energy, so in the absence of this even symmetry. And our previous argument that all these odd powers terms vanish does not hold here, because remember previously the reason why we throw away all these odd power expansion terms is because we have the zero field limit. Now the zero field limit is gone, we are at the finite field, so that symmetry is broken, so we are allowed to add this odd power terms as we like. And the lowest power that we could add is actually cubic term, because we already have this linear term. So we just add this cubic term here, and this prefactor capital C is the coefficient of this cubic term. So again, so we could just minimize the Landau's free energy density with respect to phi and find out what this trivial, non-trivial solutions are, and we get this non-trivial solutions which takes this value minus c plus minus the square root, and the little c is defined as 3 times capital C divided by 4 times b. Then we can plot this Landau's free energy density versus phi again, like what we did on the left side, but we know that this non-trivial solution exists when this something inside the square root is actually positive, okay, which means that when c squared is larger than at divided by b, okay, which means that if you revert that relation, you get this little t is less than some specific value, which I call this little t star, which is given by bc squared over a. So when this little t is less than t star, you get a non-trivial solution like this, which means that you have another minimum point developed. Okay, so that's exactly what happened here. When t is larger than t star, the square root is actually a purely imaginary number, which is unphysical. So therefore, there's no second dip or second well. But when t is less than t star, you have these two solutions, which are there representing the two minima points of this L, and one minima at phi equals 0, and another is at finite phi. But then you can change your little t to actually even lower temperature, so that the second dip is actually coming down to actually touch the horizontal 0 of the Landau's free energy, and so that this minima is actually degenerate with the global minima at 0 phi. But if you keep lowering your temperature to a temperature T1 or below T1, then that the second minima is actually becoming a global minima. So you can see that the global minima suddenly changes from 0 to a finite value without any intermediate value, because the distance between these two dips is actually finite. You cannot change the distance between these two dips continuously. So it's either or. So either you're having the global minima 0 phi, or the global minima is happening somewhere else. There's no continuous evolution of a global minima from 0 to non-zero value. As a result, this is so-called the first order transition or the first order jump. Okay, so maybe we can take a short break. When we come back, we will again make some remarks on this first order continuous phase transition based on the Landau's formalism. So let's take a short break. Summarize what we have of the first order transition, and I didn't discuss the negative side of the phi in terms of the Landau free energy density plot. So remember, when we solve this meaningful equation in the presence of the field and the cubic term, in general, there are three solutions. Okay, so I only discussed two of them, which is solution at 0 and also solution at positive side of the phi, but I didn't discuss another solution on the negative side, because you can see very clearly that in addition to phi becomes 0, there's two solutions, non-trivial solutions at this minus c plus minus square root, and if the square root is actually the real value, then we have additional two roots or solutions. And in addition to that, at 0, we have in total three solutions. So where are the third solutions? Well, it is located on the negative side of phi. Remember, this is minus c plus minus square root, and we don't discuss the plus sign, which happens to be on the right side of the phi, or positive side of the phi, but if you take the minus sign in front of the square root, you may have another solutions there. But then we need to compare the energy of those three minima points, right? So because the cubic term is actually differentiate these three different roots, because when this phi is positive and when the capital C is positive, and this is actually the positive contributions to the Landau's free energy density. But when phi is negative, and this contribute negatively to the Landau's free energy. So, which means that there is difference between these two. And we just study one of them, because either positive or negative solutions will actually minimize the Landau's free energy density at that global minimum point. So then we could just focus on one of them, okay, say the positive side. In that case, it can be the global minima. And of course, the other one will be the local minima. So of course, the capital C may be positive or negative, all right? So that's going to flip this two minima, in the opposite direction, okay? But you can figure that out, okay? Which one will give the lower Landau's free energy? And we can compare geometry of this Landau's free energy density near the transition between this first order transition and the second order transition. You notice that for the second order continuous transition, the Landau's free energy density shows a V shape and then U shape. Okay, but both U and V shapes, we have only one global minima. But once we are in the ordered phase, there are double well. There are two minima points. So we always go from one minima to at least two minima. But if you look at this first order transition, right at the transition point and after the transition, where we have developed a non-zero phi, then you can see this Landau's free energy density as a function of phi. In these two cases, there's always a double well. There's always double minima. So it's not coming from the single minima to the double minima, like this continuous transition does, but for the first order transition, at the transition point and right after the transition, the Landau's free energy density always show double minima. Okay, so this double minima transition at the transition is a characteristic of a first order jump. And the reason why you get a first order jump is because when you always have this double minima structure, then the distance between these two minima points in the Landau's free energy density plot is always a constant, a fixed value. So you cannot cross the transition and then continuously evolving this position of a local minima from 0 to a finite value. No, you cannot, because this distance between this double minima is always fixed. Okay, so that's why you get either 0 or finite. There's no something between. However, for this continuous transition, we go from the single well to double well geometry of the Landau's free energy density, As a result, near the transition point, this phi equals 0 in the middle plot is actually in the center of the U shape. You know what difference between the U and V shape? Well, the V shape, if you take the second derivative, it is positive in this case. But the U shape is actually totally flat, at least up to second order in Taylor expansion of the order parameter. So if you take the second derivatives L with respect to phi, you still get 0 when it is a U shape, which means that at the center of the U shape, it can be both a local minima and also a local maxima. Okay? So that's why you get the infinitesimal shift of your global minima from the U shape to the double well. Okay? So the distance between these two well could be as small as possibly you can tune. Okay? Because I could squeeze this double well as much as I can to actually reach this U shape. This is just a slightly. You cannot tell the difference between a U shape figure and a double well. Okay? Infinitesimally, you are able to tune the U shape and turn it into a double well, continuously evolving from one to another. So it is possible to continuously evolve the U-shape Landau's fringe density and turn it into the double well, which means that your mean field value could be tuned continuously from 0 to the finite value. So distance between this phi equals 0 and another global minima can be tuned continuously. But in the first order transition, it is not possible to tune the distance between these two minima so that you could continuously evolve from one minima to another global minima. It's not possible. You take it or leave it. You can have only two choices, but they are disconnected. So let me just make two remarks regarding to the first order transition and the fluctuations beyond the mean field. So first, the situation that we discussed earlier, that if we don't have a cubic term, then we have a continuous phase transition. And that condition is actually the sufficient condition, but it's not a necessary condition, which means that if we don't have a cubic term, indeed, we have a continuous phase transition, but not the other way around, but usually it does, not necessarily. But if you don't have a cubic term, and it's for sure that this transition can only be continuous. There's no way that this is first order transition. So the counterexample is a spin glass or rubber order parameter, which is a matrix n by n matrix, and Landau's fringe density in terms of that n by n matrix shows the cubic term, and yet the second minima occurs in the unphysical value of this q, whereas q is actually our order parameter phi. So even if we have a cubic term, as long as that solution, the second minima solution, is in the unphysical region, which shows a complex or imaginary component, then it's gone. So we don't care about this unphysical value of this phi, and we still have a continuous phase transition, despite the fact that we have a cubic term. So that is the counterexample, but there may be other counterexamples you could find in the literature. Okay? So having the cubic term does not imply that the transition is first order, but without the cubic term, it is for sure a continuous transition. And the second remark is that we ignore the fluctuations beyond the mean field theory, and the fluctuations may change the nature, the order of the phase transition, that we didn't expect. There are two examples. The first one is so-called the three-state paramagnetic or pulse model. It's the three possible spin states in the paramagnetic spin model in 2 dimensions. And we don't have time to discuss in details, but the mean field theory of the three-state pulse model predicts the first order transition, but actually it is a continuous transition. So something's missing, and that missing is actually the fluctuations beyond the mean field, which we'll discuss later. And the second example is a type 1 superconductor to normal metal transition in 3D. And the mean field theory shows it is continuous, but actually it is the first order. So either way, either the mean field theory predicts the first order, but actually it is continuous, or vice versa. But in any case, the mean field theory can have the wrong answer regarding to the nature of the transition. So we do not trust the predictions by the mean field theory. So we need to study the effects of fluctuations beyond the mean field. And what kind of fluctuations, and that's what we are going to talk about. All right? Okay, so this is just a simplest possible analysis based on the Landau's free energy density. We consider the fluctuations in the Landau's formalism based on the mean field theory. And the way that we consider the fluctuations is the spatial inhomogeneous distributions of the order parameter in the slightly larger scale. Right? So remember, correlation length C as function of temperature approaches infinity or diverges when temperature is close to Tc. And the meaning of a correlation length is the correlation or the relationship between two different spins at different spatial locations, and the length scale over which that these two spins are correlated is called correlation length. Okay, so when the correlation length grows as temperature approaches Tc, that implies all the spins or the order parameters may form clusters, at least over the length scale of the lattice spacing, which means that those spins, within the correlation length, they are ordered. Okay, above the correlation length, they may not order, but within the length scale of a correlation length, they know each other. Okay, so we could actually group a number of spins together within this, the length scale of a correlation length. So that's the meaning of so-called coarse-grained free energy. Coarse-grained means that we can actually group together a couple of spins locally to form a cluster of spins. Okay, so that from the far distance away from this lattice, you don't see individual, spin degrees of freedom. Rather, you see a cluster of spins. It's like if you take off your glasses, then you don't see very clearly those points that far away from you. You can only see just something, very blurred and form groups, and that is precisely the meaning of a coarse grain. So we actually consider the spins not just the individual spins, but they form clusters because they are correlated when temperature is very close to Tc. So in other words, you can actually split the system into the blocks. So within each block, it consists many, not that many, but a group of spins that are correlated. And the length scale over which that they are correlated, we could denote it by, say, C1 for this group 1, and C2 for this P2, and so on and so forth. So those correlation lengths for each individual group of spins may be different, but when temperature is very close to Tc, so all this correlation lengths, C1 and 2 and 3, they actually overlap. They form a big, macroscopically large group of blocks. Okay, but before the correlation length diverges, we could consider the system as a group of clusters. Okay, but within each cluster, a couple of spins. The block size is denoted by this lambda inverse, which is between the lattice constant and the correlation length at that temperature. Okay, so within each block, the order parameter is considered roughly a constant. Okay, so which means that within each block, and we can roughly consider all these spins are roughly ordered. Of course, there are some fluctuations, but we don't care so much at this point. we simply just consider that the whole lattice point consists of a bunch of patches or clusters, and each cluster we have a number of spins, which is given by this ratio between this lambda to minus d power to the volume of this little lattice spacing. So within each block, you can consider a bunch of lattice points where the order parameter is considered to be a constant within each block. But there are many, many blocks, right? So there's M1, M2, and M3, and so on. So all these different blocks may have different values of these order parameters. Capital M, lambda as function of R, represents the local magnetizations, which is some kind of an average spin moment over this each block of spin. And our Landau's free energy function is kind of a sum over all such blocks. Okay, so you can consider this effective Landau's free energy as a summation over equilibrium value of this order parameter, which form blocks or clusters. But these different values M1, M2, and 3 are still there, so we know that energetically it is not favorable to actually have very large difference between all this M1, M2 values, because in order to get the global minima, we need to actually minimize the Landau's free energy density. Remember that. But this very spatially inhomogeneous configurations of these different local magnetizations is not stable. It should not be a global minima. So we need to penalize. We need to give penalty to these different values, at least in adjacent nearest neighbor blocks. So the way to penalize this inhomogeneous distributions of local magnetization is to add the kinetic term or kind of a gradient or potential term, to be precise, over adjacent blocks that will actually increase the total energy if there is a difference between adjacent order parameters values. Okay, and we put this gradient square to actually penalize that differences between adjacent order parameter blocks and to actually make the magnetization more uniform, distributed. And therefore, we add this gradient m squared in the Landau's free energy density and to form the sum of these two, and you integrate over entire real space vector. And but then you could locally just sum over this, say, nearest neighbor blocks, and we would discuss the meaning of this so-called coarse-grained Landau free energy density, which in some sense capture the fluctuations, at least the spatial fluctuations of order parameters. So one of the things that the Landau's mean field theory neglects is the fluctuations of order parameter. But what kind of fluctuations? And spatial fluctuations is a very important one, and which was neglected in the original Landau's formalism, but somehow put it back, this spatially homogeneous distributions of the local magnetizations which form blocks or clusters of spins. And we will come from here next time to discuss how these fluctuations are going to help us to revise or update the Landau's prediction based on the pure naive mean field theory. So, and this is the starting point of the field theory, because the statistical field theory comes from the Landau's free energy density. Beyond the mean field approach, which includes the fluctuations of this local magnetizations at each block. And this is also a beginning of a so-called renormalization group approach, where you could actually sum over local degree of freedom and to form patches or clusters, and you could partially trace out this local degree of freedom in your partition function and study the effective Hamiltonian after a partial trace. You could form bigger and bigger clusters until you finally merge the single big cluster of your whole sample, and that allows you to study the macroscopic ground state of your statistical system. So we don't have class on this Thursday, but we have 2-hour class on next Thursday. And so that's call today, and I'll see you next Monday.